Yeah, okay, welcome back. Today the lecture is a continued of the finite element method lecture. So that today we are going to demonstrate the chapter 6. So yeah, in this chapter we are going to handle some 2D system. Yeah, first is a plane stress and second is a plane strain. So compared to the 1D system, I think that 2D system is more complex. However, the equation, our equation is similar compared to the 1D cases. So that we are going to derive the 2D equation as a partial different equation form. So I think that the plane stress and plane strain concept I think that you guys already learned the last year from the Professor Yang, so that I'm going to details about the theory. Today we are going to demonstrate the driving the stiffness equation in the 2D system. So today running object is a review, summary of some plane strain and plane stress, and then to consist of the FEM system. I mean that element, using the element, we are going to obtain some discretized equation. So to develop the element system, we should define some very simple element. The easiest way to define some simple element in the two-dimensional spaces, triangle is the most simplest way to define this element, but this compared to this triangle element, maybe the rectangular element more powerful to solve or obtain the numerical solution compared to the triangle element. However, it's more complex, so that maybe today I'm going to stop before to defining the element. However, so maybe next lecture we are going to learn about this CST element. But this rectangular element, I think that you guys can easily understand, but it will be time-consuming work than defining the triangle element. So maybe depending on our course schedule, I skip the details. So and then today we are going to defining the stiffness matrices in the two-dimensional spaces. So that after defining the stiffness matrix equation, and then we are applied our discretized equation into some triangle element system. So this triangle element, we are going to say that constant strain triangle element. It is because that in the element the strain value. Let's think about in the two-dimensional spaces we have 3 different strain. First strain is x direction, second strain is y direction, and third strain is maybe depending on your favorite notation, so that shear strain. This strain, however, let's back into the one-dimensional spaces. In here, let's think about one-dimensional beam or truss element. So here, we can obtain the displacement at each nodal point. However, their strain value in this simple 1D element, the strain value always returned some constant. It is because that we use some linear algebra relationship to describe the displacement field, so that the derivative of the displacement function, that will return constant. Similarly, in this triangle element, the derivative of the displacement field always constant, so that we call it the constant strain triangle element. And then compared to the constant strain triangle element, so the Q4, 4-node rectangular element, in here we are using some more nonlinear relationship. This is a linear displacement field. However, sorry. So we are going to add it one more nonlinear term, so that so in here the derivative displacement with respect to x is not constant anymore. So there are some independent variable in y in here, so that will return some nonlinear displacement field and then non-constant strain field, so that compared to the triangle element, rectangular element will give more accuracy strain field. Accuracy strain field means that we can obtain the more accurate stress value in one element, so that QPO element more useful in the two-dimensional analysis. However, the this constant element is easy to use. However, sometimes let's think about, sometimes in the two-dimensional spaces we have those kind of circuit model, or rectangular shape structure. In the rectangular shape structure, QPO element can be easily used. However, in here, let's think about this part. These curved shapes cannot represented by the this rectangular element, so that triangle element more easy to use it. So that first, and also easy to derive our Stephen's matrix equation, so that maybe the today or next lecture we are going to learn about the CST element first. However, a QPO concept is we added one more nonlinear term. So we can use the two-dimensional analysis for the FEM. So two-dimensional element can be defined, or three or more nodes to describe the two-dimensional spaces, so that, for example, those kind of plate, so that the elements are connected node, and then they share some edges. So to defining those kind of two-dimensional element, we need some basic assumption. The solid structure is continuous structure. So, and then to designing or made model, we have one more assumption. That first assumption is plane stress or plane strain. I think do you remember what is the concepts of the plane stress and plane strain? I think that most easiest way to remember the concepts of the plane stress is some values are equal to 0 in here. What is this? Plane stress. Stress. In two-dimensional spaces, we can indicate the y and x direction, but x g direction is negligible. That means that plane stress, in the g direction, stress always equal to 0. Plane strain, means that you can easily memorize the strain in g direction is always equal to 0. So that actually there are many stress related to the g direction. So maybe shear stress in direction always equal to 0. Similarly, all strain related to the g direction is equal to the 0. This is a very simple way to the mathematics meaning. So plane strain. What is the plane strain? Plane stress. First, plane stress is defined to be state of the stress where the normal stress and shear stress is directed perpendicular plane are to be 0. That means that all normal direction, for example, g direction always equal all stress value equal to 0. So that means that, yeah, what is the cases? Yeah, so yeah, if we have a very thin plate, yeah, for example, paper. Yeah, so when you apply some tangential forces, yeah, you can feel some resistance. Yeah, that means that, yeah, in this direction, the stress exists. However, to the tangential direction, sorry, yeah. So can you push or pull the paper? Yeah, so you cannot apply any push or, so you can feel some resistance. That means that, yeah, in the g direction, stress always equal to 0, so that we can assume that very thin solid structure is a plane stress state. So this is a basic assumption. And then compared to the plane stress, yeah, plane strain is a very thick solid structure. So that means that in the g direction, strain always equal to 0. It is because that let's think about this solid rod or truss, that this length is infinitely long, so that when we apply some tensile load in this solid structure, so that this solid structure will deform slightly. However, the total length is also infinitely long, so that, yeah, these two values are similar. So that, yeah, this solid structure, we cannot say that the strain is equal to 0, nearly 0. So that, yeah, that means that, yeah, plane strain, yeah, representative of very thick some solid structure. So yeah, we can use those kind of very long rod or some solid structure. So at that time, so that in the g direction of the displacement negligible, that we can analyze only cross section area deformation. So that we can, at that time, we can use a plane strain assumption. However, if we have a very thin solid structure, we should assume that this solid structure is follow the plane stress assumptions. Yeah, this is a basics. So that, two representative, or illustrating the two-dimensional states. So that we need the three independent stress variable. First is a x direction stress, and second is a y direction stress, and then this is a shear stress. Yeah, also we have other variable, for example, stress in the g direction, or shear stress in relate to the g direction, but yeah, in the plane stress, these three values are equal to 0. However, in the plane strain, this stress is automatically determined some specific value, so that we don't need to consider the value of the related to the g direction. So and then in the COMSOL simulation, we are going to check those kind of result. So anyway, so in the to represent two-dimensional analysis, we need only these three stress component. However, here, why we don't need the shear stress in the y surfaces, on the y surfaces in the x direction? It is because that our solid structure are in the equilibrium state. So what is the equilibrium? Equilibrium means that, force equilibrium, all summation force equal to 0, and then next all momentum summation equal to 0. So let's think about some representative volume element in the solid structure. Each solid structure experience those kind of stress, normal stress and shear stresses. So that in here, and then we are going to consider the body force in the solid structure. What is the force equilibrium? First, we should check the all forces in the x direction. So in here, so what is the forces? This sigma is stress, so that we should multiply some cross-section area. So what is the cross-section area? A, or dg, or, and then in this line is equal to the dy, so that this become the forces. And then here, this shear stress is related to the x direction forces, so that in here, so the length is equal to dx, and then thickness and dg. So, and then changing of the strain is related to the dy, so that you can edit those kind of relationship. I mean that you should edit those kinds of equation. It is because that the changings of the forces are related to the x derivative, and shear stress changings is related to the derivative in the dy. So anyway, so that, and here, this bx is also related to the body forces, so that maybe the body forces you should multiply the dx and dy and dg, and total volume of the solid structure is related to the acceleration of this system, so that rho is related to the mass, so unit mass, so that, and then u double dot is acceleration in the x direction. However, we are going to consider the only static condition, so that the acceleration always becomes 0. So similarly, so in the second equation is related to the force equilibrium in the y direction. I think that you can easily derive this equation. So, and then in here we have two different shear stress. First is x surfaces into the y direction, and shear stress is on the y surfaces in the x direction. So, but when you apply the momentum equilibrium after the here applying momentum equilibrium equation, maybe, so that you guys can reach those kind of symmetric shear stresses, so that finally this tau yx become changing the tau xy, so that finally we need only 3 independent stress component. Looks like this. Actually, this 2x2 matrix is a correct form. However, in our FEM 2D analysis, we are going to use these 3 stress component. Before we go more detail, we should know that those kind of stress vector concept. So stress actually defined on the specific surfaces. So it is because that stress is depends on the direction, so that we should define some exact traction forces on the specific direction. In here, n direction is n is a normal vector of the specific direction. It is because that to defining some surfaces, you should know that n is to 1 point, and then 1 is to 1 normal direction, so that those kind of in the similar manner, some traction forces can be defined by the looks like this. So that exact stress actually stress can be multiplied each node vectors. So I think that you can easily obtain those kind of relationship 2x1 vector. So maybe n vector is representative looks like this, and then finally we obtained those kind of traction forces. And here some stress component and a specific direction normal vector multiplication can be say that some specific direction forces or stress vector. And then in the last year, I think that you guys also learned about those kind of stress concept. First is plane principal stress. Yeah, principal stress. What is the principal stress? Yeah, principal stress is some maximum or minimum stress in the our solid structure, in the two-dimensional solid structure. It is because that all solid structure, solid structure experience some stress on the specific direction. Why? Yeah. So when you define some surfaces, at that time solid structure, experience some solid, resistance or here. So however, when you're changing the angle, here, so at that time, solid structure stress can be varies. Why? So it is because that the defining the surfaces, so that but all forces, actually all solid structure in the equilibrium state. However, although I mentioned that in here x and y, actually, first or I, j, more or j or I is more correct. This is a local coordination, or this is a global coordination. In the global coordination system, solid structure are in the equilibrium state. However, their stresses are varies depending on your defining surfaces. So that at that time we need some union concept. So using those kind of way, you can obtain some stresses values. So maximum stress or minimum value. So that in here, so when you applied some tensile forces of the solid structure, at that time, those kind of defining surfaces, so solid structures into the normal direction or I and J. So I want to say that in the normal direction of the monitor. So that at that time, so stress values are very small. However, you can easily think that when you define those kind of surfaces to the perpendicular applying force, at that time, solid structures are very maximum, and other direction of the stress values are very small. At that time, we can say that the maximum this stress is a first principal stress, and then automatically, minimum stress is also defining the looks like a similar manner. So that maybe I think that Professor Yang taught you those kind of more circles. So that depending on you're defining the surfaces, the solid stresses values is representative by this way. This is a maximum and this is a minimum stress, principal stresses. So also to defining stress, we should also defining the exact surfaces. It means that we should define the normal surfaces. This normal surfaces has some specific angle, so that this stress has those kind of relationship. So maybe the stress values are equal to the maximum and 0 to a specific maximum, and then shear stress is equal to 0, so that there are no shear stress in these cases. The tangent theta equal to 0, so that what is the meaning of the tangent theta equal to 0? Maybe the theta is equal to 0. So that means that there are no rotation movement. So that, however, depending on your applying force, so that these surfaces will rotate it. So that, but why we use those kind of principal stress concept? It is because that we can easily catch the maximum stress value in the solid structure. So most mechanical failure occur to the maximum stresses value. So that means that after the calculating some stress component in any place or any direction, so that and then after the calculating those kind of relationship, you can defining the maximum direction to the maximum normal direction. That's why we learned about those kind of concepts. So however, maybe anyway, principal stresses anyway has some directional component, so that without defining the directions of the surfaces, we cannot say that the exact values of the maximum stress. However, maybe although I do not mention about the another stresses component, so that maybe when you run the COMSOL simulation, first after the running the COMSOL simulation, they first return the von Mises stresses, so that maybe in the two-dimensional simulation they also return the von Mises stresses first. So it is because that this von Mises stress this is for the describing stress value as a scalar. All stresses are representative by vector quantity, so that we have the stress values have some directional component. However, this von Mises stress, we don't need to any directional quantity, so that we can representative stress value as a scalar value, so that this so to it, and then you can easily draw the stress values in the contour plot without adding the narrow vector. So that so anyway, so however, please remember the principal stresses concepts first. So that next is a strain. In the one-dimensional cases, we define the strain is a derivative of the displacement component. However, in the two-dimensional cases, we have one more displacement value in the y direction, so that the epsilon y is a derivative of the v displacement in the y direction displacement as a function of the y, not x. So that and then what is the shear strain? First remember this is a shear strain is some displacement derivative displacement in x direction displacement as by y, and then plus, and then stress displacement in the y direction and derivative by x. This is a shear strain definition. Actually, depending on your defining the shear strain, sometimes we added those kind of half values, some or average value. However, exact strain, we can say that sometimes this is a correct value or this is a correct value. Example. However, the defining of the solid structure, sometimes we can define the strain. Strain. What is a strain? Strain is angle changings in the solid structure. However, this part, so that this is length is equal to the du, and this is equal to the dy, so that the angle change is equal to the tangential du and dy, so that, and then this part also similarly, this is a displacement and dx, dv, and then this is equal to the total length is dx and dv and dx. The total strain is of the half of the two summation. However, exact strain occur to the only single direction. This is not the pure. This is not the pure shear strain. If you apply the pure shear strain direction, I mean that those kind of deformation at that time, only occurred this angle movement occurred only this side, not this side. So that at the time, this is a correct concepts. However, depending on the how to defining the shear strain, sometimes this definition more correct. So that, but I don't know how to the Professor Yang touch you guys. But however, follow this concept in this lecture. And then, so and also our solid structure, we are considered the isotropic materials. There are no isotropicity, so we are going to consider the isotropic material. Isotropic means that we can material property, mechanical strength can be representative only two components. First is a Young's modulus, and the other second is a Poisson ratio. So that if we know that Young's modulus and Poisson ratio, we can define in the mechanical property of this solid structure. This is isotropic concept. So that, and also in the plane stresses concept, so we are going to handle the very thin solid structure. All stress values related to the direction always equal to 0, or and also we can negligible and those kind of value. So but remember the shear strains are equal to 0, but the g direction value is not equal to 0. So they have some specific values in here. So however, please skip the detail. So that, and then finally, the stress component. In the previous slide, I mentioned that we are going to use only 3 elements of the stress component, and here, so that, and also strain component has only 3 components. Maybe depending on your system, maybe I'm going to use tau xy. So that 3 by 1 and 3 by 1 vector. So that means that in here, this part is Young's modulus, but not correct. Elastic stiffness matrices. So that this becomes 3 by 3 matrices. So that in here, so that we are going to defining the 3 by 3 matrices. So that in the plane, under the plane stress assumption, the stiffness matrices can be representative, looks like this. So that I'm going to homework how to derive those kind of stiffness equation. I'm not sure that you guys derived this equation. So that maybe do you remember the compliance tensors? I mean that this is a Young's modulus, and then this is a compliance. Maybe we are normally use S. This is a compliance. Using those kind of way, maybe you guys learned about the Poisson effect of the solid structure. I mean that when you applied some external forces, this in the x direction, the lengths are elongated, but due to the Poisson effect, the length is y and g directions are shrinked. So maybe the strain, maybe the strongly proportional to the compliance tensor of the x direction, but due to the other part, maybe how can we say that maybe shrinked due to the maybe we need some minus. So in here S is equal to, but so and then similarly you can also obtain those kind of relationship in the g direction or shear strains xy and yg, blah 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 blah. So and then at that time, so we plane stress, we assume that all stress is related to the g direction equal to 0. So that, and then after the reorganizing, I mean after the collecting some values, so that we can, and then some matrix inversion can be representative, looks like this. So that I'm going to homework about how to derive this stiffness so elastic stiffness matrices. So that, and then yeah, plane strain. Yeah, for the plane strain, yeah, we assume that all strain related to the direction is equal to 0. So we can also obtain those kind of relationship. Yeah, so that's very simple concept, so that, yeah, that's going to skip. But anyway, yeah, planes, although depending on your assumption, plane stress or plane strain, the elastic stiffness matrix can be representative, looks like this. The all diagonal terms have some specific value, and also only some elastic modulus in the shear part have a specific value. However, in this shear part always equal to 0, so that, yeah, this is a more general form of the 2D elastic stiffness matrix for the 2D cases. So anyway, yeah, in the previous slide, we defining the force equilibrium equation, so that we are going to assume that the acceleration always equal to 0. So that, yeah, but yeah, we are going to consider some body force effect, but finally we neglect the body forces effect. But and then, so in here, so stress, how can we represent stress? Yeah, sigma x is a multiplication C11 and epsilon xx, and C12 and epsilon yy. So that can be changing the looks like this. And shear stress is a multiplication C33 and gamma xy. Yeah, here. And similarly, shear stress representative looks like this, and then, yeah, stress is the y direction can be representative and looks like this. And here we are going to changing the stress is a derivative displacement function field, and then looks like this. Yeah, we are going to have some slight issues on the shear strain. However, in this lecture, please just follow these concepts. So, and then, yeah, epsilon xx can be changing the du and dx, and epsilon yy can be changing the dv and dy. And similarly, yeah, shear strain and du dy and dv dx is a summation of the both two terms, so that can be representative, can be changing the looks like this. Yeah, this is a general concept. Yeah, in here we don't have any assumption of the plane stress and plane strain yet. So, and then, yeah, and then after the depending on your system, yeah, when we assume that 2D system follow the plane strain assumption, so that we can changing the elastic stiffness matrices and looks like this. And then, yeah, we can changing these two equation and looks like this. I prepared how to derive or how to obtain those kind of partial difference equation, so that I prepared here, so that maybe first you can add the elastic element of the elastic stiffness matrices of the plane strain, so that you can add those kind of component directly, and then some matrix manipulation, so that we can obtain those kind of mathematic partial difference equation. Yeah, similarly, yeah, when you assume that plane strain at that time, so that we have those kind of elastic stiffness matrices, yeah, when you adding here, so that some mathematic manipulation, finally we obtain the slightly different partial difference equation depending on your assumption. That is why I prepared those kind of partial difference equation. It is because that I already told you that FEM method in this lecture we applied FEM method into the solid structure analysis. However, yeah, actually FEM method is a numerical method to solve any partial difference equation. So that, yeah, when we have some any partial difference equation, we can apply our FEM technique to solve these kind of partial difference equation. So anyway, maybe I think that you guys in the solid mechanical lectures in last year, so I think that you only handled some force equilibrium equation, but the most important thing is this is partial difference equation. So so when you obtain the partial difference equation, all done. It is I think that you guys can easily apply the Galerkin residual method or energy method to obtain the discretized equation. So among them I choose a Galerkin residual method. All method reach the same result. So that so today just follow the how can we obtain the discretized equation. For example, local stiffness matrices of the 2D system. So let's back to the again. This is the equilibrium equation. In here we neglected the acceleration pulses. So that, and then we say that the plane stress and plane strain has those kind of elastic matrices, elastic stiffness matrices. So and then equation can be expressed look like this, and then so the strain also expressed looks like this, and then after the applying the after the changing the stress strain as a derivative displacement function, and then here in this step applied Galerkin residual method. What is the Galerkin residual method? Galerkin residual method is a residual all domain residual summation of the residual in the all domain equal to 0. However, there are no event those kind of situations, so that we added more additional weight function. So that in here I added weight function. We have a 2 PD equation. I prepared the separated Galerkin residual method. In the final step, I'm going to combining these two equations, but in this in the starting point, I solved this equation separately. Here, first equation and looks like this. Actually, we already know that. What is this? We are going to use some wave function. So that, I'm going to explain in the next slide. So that anyway. In here, when you apply the those kind of relationship, what is this? This is a second derivative of the displacement u. However, just think about how in the previous lecture how we defined the displacement field. We defined the displacement as a linear function. But in this stages, we have one more additional dimension, so that we are going to use also added this independent variable y. But we are going to use anyway we are going to use a linear displacement field like this way. But in this time, however, anyway, after the derivative of the displacement field, we obtained those kind of constant value. Second derivative always return to 0, so that we cannot apply this second derivative equation indirectly, so that we need some more techniques. What is the technique? First technique is integration by part. So that what is the integration by part? So what is the integration by part? I prepared the equation again. So in previous slide, so we have those kind of equation with some arbitrary wave function. So what is the integration by part? In Korea, I normally use 그적 미적. So that how can we use it? 적분, integration wx, and then remains 그적 미적. So that yeah, first sorry, I is so that this is an integration whole domain. So that first, yeah, we need integration this part. So that yeah, so that wx and then integration once, but yeah, they changing the surfaces domain, and then minus, and then derivative this part, and then integrate this part, and then same volume integration. Yeah, this is a result. The looks like this. So, but when you integrated here, so that yeah, to integrate the surface's specific normal direction, we need some the multiplication the normal direction, so that they added some those kind of surfaces direction here, so that so integrate after the applying integration by part, so we obtained those kind of equation, and then this part we don't need to any changes in here. So anyway, yeah, but in when you check more detail, yeah, here, yeah, this part is very similar of the traction forces. Yeah, traction forces representative by the stress, normal stresses in the x direction and shear stresses in the y direction. So that stress in the previous slide we mentioned that the this part is a sigma xx, and this part, yeah, until here, so that this part, yeah, shear strain, shear stresses, so that we can changing this part as some traction forces. Actually, yeah, in the one-dimensional cases, yeah, this part is can be the what changing, yeah, some specific nodal forces. Similarly, in the two-dimensional cases, in the two-dimensional spaces, yeah, they have yeah, we already know that, yeah, we are going to use some rectangular element, so that, yeah, if you added some forces, yeah, these forces can be applied on the surfaces. Yeah, these forces also we can say that distributed forces. So anyway, so that, yeah, this can be expressed it looks like this. Some traction. Traction is actually not forces. Normally I say that traction forces, however, exact concept is traction is a similarly stresses. So that so anyway, so this part representative some boundaries forces, and then this part is some governing equation. This part representative body forces. So yeah, we obtain those kind of relationship. So, and then similarly in the second equation, yeah, in here, yeah, second PD, a second partial difference equation also can be applied integration by part, so that we obtain the similar relationship. Yeah, first is traction forces on the y direction, so that, and then this is our governing equation, and this is a body forces in the y direction. So, and then, yeah, finally we obtain those kind of two different equation. Yeah, first part is a governing equation, and second is the surfaces traction forces, and third is body forces at specific x direction in the y directions. Yeah, this first equation represent the force equilibrium in the x direction. In second equation, representative pursue equilibrium in the y directions. So yeah, so we obtained those kind of weak form equilibrium equation. So and then we are going to changing this equation as discretized form. Yeah, what is the discretized form? I mean that our displacement, yeah, in the one-dimensional cases, we say that, yeah, this is they follow some linear relationship. Yeah, however, we say that, yeah, we can changing those kind of relationship. Yeah, n1 and n2 is a shape function. This, yeah, is they containing independent variable axis, so that, yeah, normally we use those kind of relationship. So yeah, similarly, yeah, we are going to use this interpolation function. Yeah, so this representative n1 and n2 and n3 and n4. Yeah, it is, yeah. In this stage, I'm not sure how many interpolation function can be used. It is because in the 1D cases we freely defined our element, number of the element or number of the node in the element. But in here we don't define yet, so that I'm not sure how many interpolation function can be used. So anyway, similar form we can use for the discretized formulation, so that V also can be expressed the same. We can use the same interpolation functions, so that in the matrix formulation, yeah, here, so that, yeah, in the n1 and u1 and second value we don't need any v element, so that n2 and u2, so that, yeah, so this is the same formula in the, yeah, they can combining looks like this. And then, yeah, what is the strain? Yeah, strain is yeah, sigma xx is a derivative u as by x, so that, yeah, this is a correct form. Now, what is the strain y direction? So that, yeah, this is a correct form. And what is the shear strain? Yeah, this is a u as y, v by axis. So that this, yeah, is a same form of three equation. But in the previous slide, we changing this u and v displacement value and as discretized the form, so that, yeah, so that, and then you can multiply this equation, looks like this, and then we obtain those kind of relationship. Yeah, what is this? Yeah, this is a B matrices. In the one-dimensional cases, we say that strain is a B matrix and U value, so that same in the two-dimensional cases also. However, the detail element are more complex than, yeah, here. So anyway, yeah, we obtained those kind of relationship, and then after then we are going to apply this equation. Yeah, first, before we applying some discretized formulation, so that we are going to combining these two equations. Yeah, these two equations you can easily combine. Yeah, it is hard to obtain, so that, but anyway, you can easily, yeah, this part is a multiplication of this relationship, but and then wx and wx and wy and wy also is a multiplication of this part, this relationship. So anyway, yeah, just trying to this is the same equation. So similarly, next slide. So that, yeah, before we using this, yeah, we should changing the discretized formulation, so that, and also in the wx and wy is an arbitrary function. However, we are going to same interpolation function as a weight function. Yeah, it's more, yeah, sometimes it is hard to understanding directly first, but just think about this wx just follow the same form of the wx. In here, what is the wx? Wx is yeah, wx1 and wx2, yeah, same for, yeah, blah 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 blah. So the same formula of the displacement value, so that, however, their form is slightly different, so that we need those kind of expanded vector actually matrices form. So that, and then they due to the some transpose matrices, so that we can use finally we obtained those kind of relationship. So that so that after the applying the transposes in here, so that matrix, these matrices can be multiplied each other. And also in here, actually we already know that this part result, what is this? This part result in the B matrices in the previous slide. Similarly, although their form is slightly different, however, the result also similar of the transposes of the B matrices. So that so you can check the here. This is a B with transpose. This is also B. So that finally, in here, we can say that this is elastic stiffness matrices. So that finally, in the integration part, BdV is the same form of the truss or beam element of the general stiffness, local stiffness matrices. So that although this arbitrary function and the displacement vector remains in the outside. Similarly, traction forces can be combining each other, so that we can use those kind of same vector arbitrary function. So that, and then using the here, so that in the previous slide we described Wx can be representative N1 and then Wx. So similarly, so that they use those kind, they return those kind of shape function, and then with arbitrary displacement vector, actually matrices, and with traction, and not forces, traction stresses in here. Also, body force can be combining similar manner, so that this part can be changing the some return the shape function, and then some arbitrary displacement matrices, and then finally we obtain those kind of relationship. But in here all equal to 0. First time, in the Galecki residual method, so that they use a arbitrary function Wx and Wy, so that they can be arbitrary value. So that if this value can be arbitrary, any values in here, to become 0, what is the way? The remaining things is the way, only way is to the remaining part become 0. Not independent, not each part is 0. I mean that we can combining this arbitrary matrices, and then with the bracket, so that the inside bracket become 0. So this is only way to become this equation can become 0. So and also sometimes we can easily cancel out. It is because that you can multiply the inversion matrices in the right hand side, and also after the multiplying that inversion matrices in the right hand side, this also always return to 0, so that you can easily depending on your favor, you can easily understand. So that finally we obtained those kind of relationship equations. So that this is a final form of our discretized equation in here. So maybe we can reorganize the displacement vector, and looks like this, and then sometime we can negligible the body forces, so that we can obtain those kind of relationship. Here this part displacement u, and this part is a local stiffness matrices, so that we can say that this equation general stiffness matrices of the 2D similar 2D cases, or in the 3D cases, yeah, you can easily, yeah, maybe B with integration total volume, so that, yeah, you can, sorry, yeah, maybe I make some, yeah, we need some thicknesses. I made some mistake. It is because that, let's back into the again. Yeah, I think that I make some mistake. Yeah, we should consider the thickness actually, but yeah, I assume, yeah, just assume that thickness equal to 1. So next time I'm going to say that, yeah, here local, yeah, we should consider the thicknesses in here, so that, yeah, I neglected already of the thickness in the 2D cases, so that, so just think about thickness is already equal to 1, but depending on, I assume the thickness is 0.5, so that at that time you should consider the thickness in here. So anyway, so yeah, here the local stiffness matrices and looks like this, and the B matrices can be say that here. So it is because of strain. How can we define strain? Yeah, we define strain looks like this, and then they representative looks like this, plus dv dx. So these u values can be changing the shape function with u value, so that, yeah, B matrices can be say that looks like this. So, and then in here, this is a shape functions, and then, but in here we can say that how many nodes are used for the to representative this local stiffness matrix in the two-dimensional spaces. However, in the three-dimensional, when we use a triangle element, the number of the degree of freedom is 6. Each node has a 2 degree of freedom, so that each displacement value has a 3 element each direction, so the total 6 degree of freedom. So that at that time we can say that our forces vectors looks like this, and shape functions can be used n until n3. If we use, when we use 4 node element, so that we should use n4 4 different shape function, so interpolation function. So after the adding, applying the after the selection of the element, so that we can finally, yeah, obtain the local stiffness matrices of the 2D cases. So that in here I added the thickness value in here. So yeah, this is today the lecture, so that maybe next lecture I'm going to continue the defining of the constant strain triangle element. Yeah, constant strain triangle element, so that maybe please follow the driving the local stiffness equation. If you are confusing the driving the local stiffness matrix in the two-dimensional spaces, just to remember this B matrices and the final result. So this is today the end of the today's lecture. If you have any question, please follow the detail. 예, 그리고 시작할 때 제가 공지를 많이 안 드렸는데요. 먼저 중간고사는 없습니다. 예, 중간고사 없다라고 여러 번 강조드렸고요. 저희가 아마 기말고사랑 그다음에 콘솔을 활용한 이제 기말 프로젝트가 동시에 나가니까 아마 하나는 중간고사 같은 느낌, 하나는 기말고사 같은 느낌으로 준비를 해주시면 될 것 같습니다. 그리고 강의가 전체적으로 학기 말까지 온라인 강의로 다 대체되었기 때문에 이미 여러분들 다 아시고 있을 거라 생각을 하고요. 예, 조금 힘드시겠지만은 필요하신 것들은 그때그때마다 질문을 해주시면은 제가 바로바로 답해드리고 있습니다. 많은 분들이 아직 질문을 하나도 안 해주셔가지고 좀 심심합니다. 예, 많은 질문 부탁드리겠고요. 예, 다음 시간 이어서 진행하도록 하겠습니다.